Question 10 is coming from circular measure. The diagram shows a sector ABC, which is part of the circle of radius A. The points D and E lie on AB and AC respectively, and are such that AD is equal to AE is equal to KA. We can see this one here, where K is less than 1. So the line DE divides the sector into two regions which are equal in area. Part A. For the case where angle BAC is pi over 6 radians, find K correct to 4 significant figures. They have given us the angle BAC as pi over 6. Okay. Now there is something they said here. The line DE divides the sector into two regions which are equal. You see that? So that means the area of this one here is equal to the area of this one here. So what is the area of triangle ADE? So this one is going to be equal to a half, then times this side and then this side. That is KA times KA, then sine of the angle that is in between, which is formed by these two sides. And we are given pi over 6. So pi over 6. Of course, this one is a half, then times a half. That one will give us a quarter. Then K squared, A squared. Now, we also need to get the area of this big sector, because for us to get the area of this one, I'll get the area of the big sector here minus the area of this triangle, okay? So area of sector ABC. Remember, area of the sector is a half r squared what? Theta. So we shall have a half, the radius is this A here. So we shall have A squared, and then the theta is pi over 6, meaning we are going to have pi over 12, then A squared. He said that area of triangle ADE is equal to area of BCED is equal to this one here. So this simply implies that the area of this sector ABC is twice the area of this. Not so? Yes, that's what it means. So therefore, area of sector ABC is equal to 2 times the area of triangle ADE. So area of the sector is pi over 12 of A squared. Then here we have 2 times area of the triangle is a quarter, then K squared A squared. They said we find the value of K. Now A squared is on both sides, so that one can disappear. This one can go. So we shall have pi over 12, which is equal to, this one can go to a half of then K squared. So if I can cross multiply here, we shall then have 2 pi over 12, then under the square root will give us K. So what will be K to 4 significant figures? Square root of 2 pi out of 12. This one will give us 0.7236, and the rest of those figures, but to 4 significant figures, I'll write 0.7236. 0.7236. That is 4 significant figures. Now, if you write your answer to 3 significant figures because you are used to that, you're going to get this one wrong. They have told you, remember they say unless a different degree of accuracy has been stated. So we stick to the 4. Part B, for the general case in which angle BAC is equal to theta radians, where theta ranges from 0 to pi over 2, it is given that theta over sine of theta is greater than 1. Find the set of possible values of k. Now, from the previous calculation, we have seen that area of the sector ABC is equal to 2 times the area of triangle ADE. Okay, and the area of the sector, we have seen it is a half. The radius is a, then square, then times the theta, then is equal to 2 times area of the triangle is a half, then times the radii. Okay, the two lengths were KA and then KA. So we are going to have times KA times KA, then sine of the angle in between them, which is theta. Okay, so meaning we can have a half here of a squared theta, which is equal to, here we have k squared a squared, the sine of theta. Now k squared, from here, of course the a is going to go. I'm going to express k squared in terms of the theta. So we are going to have k squared, which is equal to 1 over 2, then sine theta. Actually, instead of writing the one here, there is a theta. Okay, there is this theta here. So we shall have theta over that. You see that? Now, they said that theta over sine theta has to be greater than 1. You first cross multiply, and then you have 2k squared is equal to theta over sine theta. So since we have theta over sine theta has to be greater than 1, now that means our 2k squared must be greater than 1. You see that? Now this one is like a quadratic equation. So we are going to solve a quadratic inequality. So I can divide all through by 2, and then I bring the one this side, so it will be k squared minus 1 over 2 greater than 0, right? And to transform this one into the completed square format, I can have k squared, then minus, this one can be 1 over root of 2, then squared. Not so. Yeah, so that when I square here, I get this. And then this one can be k plus 1 over root 2. I'm now factorizing, then k minus 1 over root 2. So of course, when I equate this one to 0, I'll get this one here giving me negative 1 over root of 2, and then this one will give me positive 1 over root of 2. Now, since the coefficient of k squared here is a positive, that means I'll have a U-shaped curve. Okay, and then these are the critical values. So we have negative 1 over root of 2, and then we also have 1 over root of 2. Okay, then from there, we are supposed to pick the values. This one is positive. So we have positive here, and then minus. So meaning we are going to get our k less than negative 1 over root of 2. And then we also have k greater than 1 over root of 2. Okay, but then up here, they told us from part A, because this one stems from A, they said k has to be less than 1. So if k is less than 1, we are going to, I can add here a 1 and also add here a minus 1. You see that? Now, since we are going beyond this one here, we are going this way, then it has to be within this region. Okay? It shouldn't go beyond 1. So if you leave it like this, this one is open, it goes up to infinity. Okay? So I will write 1 over root of 2. So I'll take this region here. 1 over root of 2, then less than k, less than 1. I'm not going to take this one here because k here will be a negative, okay? And if k is a negative, you check back here, k is a scalar that is multiplying here, and we cannot have negative lengths. You see that? So that's why we are only taking this one here, and then we dismantle this one. So that is that.